So amplitude 10, then the maximum velocity 100 centimeter per second. Then you have to determine the displacement from the mean point. If its velocity is 50, so find displacement y or x when velocity is equal to 50 centimeter per second. So here you are given velocity to find the displacement. So you must use v is equal to omega times a squared minus y squared. Okay, and when you substitute your velocity 50, you must determine the angular velocity when the amplitude is 10 minus y squared. So in order to find y, you must get omega. Now, we also have a relationship between maximum velocity. The maximum velocity which occur at the mean point is always omega times the amplitude. Because at maximum value, y is 0. So knowing A and V max will help us determine omega. So 100 divided by the amplitude, which is 10, would give us 10 radian per second for angular velocity omega, or the angular speed. Therefore, once we have omega, we can find y. So we have 50 is equal to 10 times the amplitude is 10. So 10 squared minus the displacement at that velocity, that. So we must eliminate, yes, when we divide through by 50, we have 5 is equal to, when we divide through by 10, we have 5 is equal to root of a squared, which is, 10 squared minus y squared. Then we think of eliminating the root sign by squaring both sides of the equation. So we'll have 10 squared minus y squared is equal to 25. Okay, therefore, y squared will be equal to 10 squared minus 25, which is equal to 75. 10 squared is 100. So 100 minus 25, 75. So y therefore would be equal to the square root of 75. And this is 5 root of 3 centimeter. Or you can change it to decimal to have that. So it means that when velocity is 50 centimeter per second, it will occur at a displacement which is equal to 5 root 3. And 5 root 3 is equal to 8.66 centimeter. Okay, so that is the solution to the first question. And most of you got this correct. Question 2. A simple oscillator has a period of 0. So question 2, here period is given as 0.01 seconds. And the amplitude A is equal to 0.20 meter. The magnitude of the velocity at the mean point. And here, it's all about remembering that maximum velocity is always at the mean point. So if you are to find velocity at the mean point, then it's clearly the maximum velocity. And this is given by omega times the amplitude. Omega is also 2 pi over the period. And we have everything. 2 pi divided by 0.01 times the amplitude, which is 0.2 and 0.20. Okay, so we have 200 pi times 0.2 is 2 on 10. See, we have 40 pi, which is also, I think, 120. Is it 123 or 27? Is it 123 or 27?
0.6.
Okay. Approximately meter per second. Question 3. Question 3. If the length of a simple pendulum is increased by 2%, then the time period changes by, okay, so it was about a change. Okay, so if the length of a simple pendulum is increased by 2%, so L1, please, a minute, I'm coming in. Okay, so the original length is equal to 100%, or L1 is L, and L2 is increased by 2%. So L2 will be equal to 102% because it's 100 plus 2%. Okay, so if T1, we said that T is directly proportional to root of L. Therefore, T2 over T1 will be equal to root of L2 over L1. Okay, and so when we substitute our values, we have L2 would be root of 102% is 1.02 of L1 divided by L1, which is 100%. So we have this to be equal to root of 1.02. And what is the square root of 1.02? What's the square root of 1.02?
1.01.
1.01 of T1. So this will be the new value of T1. So the change is actually this, okay, 1.01, which is the change in the period will be equal to 101%. So if the length changes by 2%, okay, then the period would also change by this percentage, which is 101% or 1.01 in fraction. Then the next question, if the period, and you see, good, that reminds me, when I was looking at this question, my observation were, you see, it's the same string whose length is being varied. The original length 100%, the new length increases by 2%, so 102%. Meaning that gravity and 2 pi, those values are constant. So instead of going over using this formula, T is equal to 2 pi root of L over G, this and this are constant. So simply T must be directly proportional to root of L. Okay, so T1 will be equal to root of L1, and so T2 must also be directly proportional to root of L2. And so when you take the ratio of the periods, then you have the ratio of the length, meaning this constant 2 pi and root will cancel out when you take the ratio. That is why you are not to repeat 2 pi root of L, but just pick this and then work with this. Class, are you okay? Class, are we okay?
Yes.
Question 4, the same thing, the same concept. If the period of oscillation of mass m, so we have mass m is 1.0 seconds. Then when the mass is changed to 4 times the initial value, meaning this is the new mass is 400% of the initial value. What will be the period? So this question as well, the same spring. So K is constant. The spring constant does not change. So all that is being varied here is the mass. So use, since T is equal to 2 pi over M on K, it means that T is directly proportional to root of M. We know T is inversely proportional to 1 on root of K, but we are not varying the spring. So we wouldn't have different K. So we use this for our analysis, meaning T1 must be directly proportional to root of M1, and T2 must be directly proportional to root of M2. Okay, this is for constant K. And once you are not varying the spring, K will be constant. Then take the ratio of the periods. T1 over T2 would be equal to square root of M1 over M2. T1, we are told, is 1.0 seconds. T2, we don't know. This is equal to M1 is capital M, whereas M2 is 4M. So you realize that M will cancel out. So 1.0 over T2 would be equal to 1 over root of 4. And since root of 4 is 2, we'll have T2 being equal to 1.0 seconds times 2, giving us 2.0 seconds as a new period, okay, when the mass changes by that amount. So this is, but the good news is that a lot of you got it right. A lot of you got it right. I'll also send another sample question, and this time around, increase the level of the difficulty to see how you can play along. Is there any question? Is there any question? Okay. if there is no question, then let's quickly finish this concept on energy possessed by a body executing simple harmonic motion. I think that's the last area under this concept that must be considered. Energy possessed by a body executing simple harmonic motion. Class, let me quickly take attendance, okay, and then get back to the house. I'm doing that so quickly. Oh, this thing is wasting my time. Let me continue. When it stabilizes, I'll come back to it. So an oscillating body possesses kinetic energy by virtue of its speed. So it possesses an oscillating body possesses
Recording in progress.
Give me a second, I'm coming. Okay, so an oscillating body possesses kinetic energy by virtue of its speed. Kinetic energy by virtue of its speed and potential energy by virtue of its position. Hey, who is that? Please mute yourself. Let me mute all before he mutes all of us. So potential energy by virtue of its position. So its kinetic energy is due to its speed, and its potential energy is due to its position. So let's pick this energy one after the other and analyze. KE is equal to half mv squared. Half mv squared. Meaning that this is by virtue of the object's speed. So wherever, or implying that wherever speed is maximum, kinetic energy must also be maximum. So implying that KE will be maximum at a point V is also maximum. Now, for an oscillating body, at what point is its speed maximum? At what point during oscillation is its speed maximum? Yes, anybody to help? Jojo?
At the rest position.
At the rest position, or at the fixed point, being point, or equilibrium position. Okay, so clearly, it also means that the kinetic energy will be maximum at the rest position, mean point, or fixed point. Okay, and where do we have the velocity or the speed being minimum? Any lady to help? At what point is the speed minimum or zero? At what point is the speed minimum or zero? Any lady? Another hand is up. Okay, Refua.
Please, at the extremes.
At the extremes. Okay, so once V is minimum at the extreme, then clearly kinetic energy would also be minimum or zero at the extremes. Okay, now kinetic energy KE can be expressed as half mv squared. But let's look at V. If we do this with respect to time, velocity with respect to time is equal to A omega cos omega t. So if we want to express this as such, then kinetic energy would also be equal to a square of this would be half mv squared. So v squared is A, let me change small a to capital A, omega cos omega t all squared. And KE would be equal to half m omega squared A cos, okay, half m omega squared A squared, okay, cos squared omega t. This is the kinetic energy in terms of time. Kinetic energy with respect to time, which we can also rearrange to be equal to half K A squared cos squared omega t. This is because spring constant K is also m omega. So in place of K, spring constant K is equal to m omega squared. So we are only replacing this part of it with K. So either you express it as this or this. Please, is there any issue here which we can address? So this becomes kinetic energy formula with respect to time. If you are writing, quickly do that so I flip to the next page. When you are done, let me know so as to continue. Or can we continue before, because I'm recording?
Yes, sir.
Yes, please.
We can also have the kinetic energy formula with respect to displacement. And if we are doing that with respect to displacement, you know, or I said displacement, velocity. Velocity of an oscillating body with respect to a displacement is given by omega a squared minus y squared. And when we square both sides of the equation, we'll have omega times a squared minus omega, v squared, if we square both sides, omega squared times a squared minus y squared. So when we substitute this into kinetic energy, which is half mv squared, this will also give us half m times omega squared a squared minus y squared. So that when we simplify it, we have half k times a squared minus y squared. This is the kinetic energy formula with respect to displacement. And we can use this to ascertain where Ke is maximum and Ke is minimum. Okay, and that is when y is equal to 0, we'll have Ke to be equal to half K A squared. And this gives us the expression of maximum kinetic energy. And when y is equal to the amplitude, if y is equal to the amplitude, we'll have Ke being equal to half K A squared minus another A squared. And this will be equal to 0. So this confirms that, yes, kinetic energy is maximum at the mean point, maximum at the mean point or rest position, and it's minimum at the extremes. Okay. What about the kinetic energy, potential energy? We are saying that the potential energy possessed is by virtue of its position. Position is displacement. But for potential energy, we have two different kinds of potential energy. We have elastic potential energy, and we have gravitational potential energy. Gravitational potential energy. The elastic potential energy is discussed whenever we are dealing with springs. So we talk about elastic potential energy for springs. So let's look at what goes into elastic potential energy. We define elastic potential energy as the work done in stretching or compressing elastic material. So the work done in stretching or compressing elastic material is what we are defining as elastic potential energy. Okay, or it is also the energy stored in stretching or compressing it. So let's have a spring. When the spring is not being stretched, this is the length. If the spring is stretched, we are stretching it by suspending a load. When the spring is not being stretched, the restoring force acting on this is equal to 0. Okay, when we are not suspending any load, there is no restoring force, there is no load, and so there isn't any restoring force acting on the spring. Class, are you following? Are we following? Okay. If we suspend a load, there is a restoring force F, which is equal to Hooke's law. K times the extension, there's the extension within the spring when we suspend the load, E. So the restoring force is given by the spring constant times the K, the extension E. So
Yes,
we are saying that the work done in stretching, and we know work done to be equal to force times distance. Our distance here is equal to the extension E. Okay. But because we are looking at two different situations, the force must be equal to the average force. How do we calculate the average force? The average force, F average, is equal to, what is the force when there is no load? 0. What is the force when we suspend a load? The restoring force, KE. This divided by 2, average. Therefore, the work done in stretching this will be equal to the average force, which is half KE times the extension E. Okay. Therefore, the work done in stretching this by the load is given by half Ke squared. This work done in stretching the spring is what we refer to as the elastic potential energy. Elastic potential energy of the spring. So sometimes shortened as just E, which is equal to half K times the square of the extension. So if the extension is represented by Y, then it becomes Y squared. That is how to determine elastic potential energy. Elastic potential energy. And since K is equal to M omega squared, elastic potential energy is also equal to half M omega squared times Y squared E. And so by this, we can determine where elastic potential energy can be maximum and where it can be minimum. This is elastic potential energy is directly proportional to the square of the extension or the displacement. So it's a factor of the displacement or position of the body. So clearly it means that at the mean point where Y is equal to 0, elastic potential energy will be 0. And at the extreme where extension is equal to the amplitude, elastic potential energy would also be maximum. Please, are we okay? Class, are we fine?
Yes, sir.
If you are not clear with something, let me know so as to explain before we move on. If you are not clear with something up to this stage. So the elastic potential energy is the work done in stretching or compressing the spring. Okay, and it is the work done is determined by the product of the average force. So we look at average because we look at two scenarios. When there's no load, there's no restoring force acting on the spring. When there is load, there is restoring force. So we look at this average forces. Okay, that is why we have F average giving us 0 plus KE divided by 2, and that is equal to half KE. This is the average force. And since work done is force times distance, the average force times the distance by the load, which is the extension, and that ushered us into this. And the next point is that maximum potential energy is equal to half M omega squared times E squared. This is because for maximum to occur, Y must be equal to the amplitude. And this occurs at the extreme. Okay, at the extremes. Okay. The minimum elastic potential energy is always equal to 0, where the displacement Y is equal to 0. Okay. Now let's look at the gravitational potential energy. So this has to do with springs. Okay, we discussed elastic potential energy for springs. For gravitational potential energy, GPE, In our normal calculation of gravity, potential energy, if an object, if there's the surface of the earth, and then an object is moved to a height h above it, this is the object. What is the distance from the surface of the earth to the position of the object? This is h. If we want to calculate the potential energy, it is the work done in moving the object from one point to another point within the gravitational field of the earth, or within the earth gravitational field. For the work done in moving an object from one point to another point within the gravitational field of the earth is what we are calling as the as potential energy. So how do we calculate it? Every work done is force times distance. Come in. I just want to take another. Come in, I'm taking attendance. Okay, so if we are calculating this, the force acting on the body is due to its weight. Okay, is due to its weight, W. So the force is mg. What is the height within the gravitational field? H. Hence, mgh. This mgh thing, which is the work done in moving the objects from the surface of the earth to any position within the gravitational field of the earth. This is what we are calling as potential energy. Okay. Now, when an object is moved from one point on the surface of the earth to another point, we don't talk about the potential energy. This is because the movement, the object's position must be within the gravitational field of the earth, which is, okay, towards the center or the surface of the earth. So if you are moving linearly, you are not moving within the gravitational field, and so there is no potential energy. Is that okay? So if it's about gravitational potential energy, then we look at the motion of a simple pendulum. The motion of a simple pendulum, a string. When an oscillating pendulum, which is fixed at a point, and then there's a length of the pendulum. When it's like this, we are talking about it being in the rest position or the equilibrium position. Now, when this is moved through an angle theta, you realize that when it is moved through an angle theta, there is a vertical movement of the object. This is L. So when you trace its position when it was at rest, to its current position, you realize that, I'm coming, let me undo it and do it. Okay, good. You realize that it has covered a very small vertical height. This is that small vertical height covered. This is moved through an angle theta. Okay. This is moved through. So we are looking at this. We are interested in this small vertical height because getting that vertical height movement would help us calculate for the gravitational potential energy, which is mgh of the object. Now, this L, this is the length of the string, and it is the same as this length from the center. So if this is L, from the center to the fixed point is also L. Okay, meaning that L, which is the length of the string, can be equal to x. X is the distance from the fixed point to this position. So L is equal to x plus h. Please, L is this whole height. So the adjacent to the angle, which is x, plus that small height h, must be equal to the length. But when we take this side is perpendicular to this, if we take cosine of the angle, cos x would give us, cos of theta would give us x divided by L. So that x will be equal to L cos theta. If we make x the subject from here, we have x giving us L minus h. Please, if you have a question, let me pause so you ask. If you have a question here. All right. So if x is equal to L minus h, let's substitute this in place of this equation. We have L minus h equal to L cos theta. Therefore, that vertical height h would be equal to L minus L cos of theta. So that L out, we have 1 minus cos of theta. And once we have an expression for that small vertical height in terms of the length of the string and then the angle of tilt theta, we can now calculate for the gravitational potential energy. So gravitational potential energy, which is the work done in moving it within the gravitational field of the Earth, will be equal to mg times h, and h now is L times 1 minus cos of theta. So if it's an oscillating body, which is about the motion of a simple pendulum, then its gravitational potential energy must be determined by this. Okay, mass of the bulb, G is due to gravity, times the length of the string, times 1 minus cosine of the angle of tilt. I'll send you a question to this effect. So note how to calculate for elastic potential energy elastic potential energy is equal to half m omega squared times the square of the extension or displacement. And gravitational potential energy can be determined by this. As for the velocity, for a simple pendulum, at any point, there is velocity, which can be stated for non-uniform and uniform. If it's uniform, is seen as a uniform velocity motion, then at every position of the oscillating body, okay, you must be given its velocity is the same. But if it's non-uniform, okay, it will also be at every point, the velocity would also be stated in a question. After all, your level only talks about uniform circular motion. So we always assume the body to be oscillating with that constant velocity. Okay. All right. So this is it with gravitational potential energy and elastic potential energy for an oscillating body. And this is for springs. And this is for simple pendulum. Now, what is the total energy? The total energy of a body executing SHM is equal to E total is equal to its kinetic energy plus its potential energy. So this is equal to the total energy is the mechanical energy. Mechanical energy is the sum total of PE and KE. This energy is always for an oscillating body, the total energy is always conserved. The total energy is always conserved. Class, if energy is said to be conserved, what does it mean? Can somebody help? What does it mean to say that energy is conserved? Yes, anyone? Anyone? I have a lot of you here, so if energy is said to be conserved, what does it mean? Energy conservation. Okay, Maria.
It means that all of the energy that was initially in the system will remain inside the system.
So
it will just change from one state to another.
Or nothing will be lost.
Yes, please.
Nothing will be lost. So if energy is conserved, then the energy is maintained. The energy is said to be maintained. Okay. Let's look at how this will be maintained. Let me show you the motion of a simple pendulum and the motion of a loaded spring. So if you haven't seen a simple pendulum, the motion of a simple pendulum before, here you go. So this is the motion of a simple pendulum. Okay. This is the pendulum bulb. The pendulum bulb is here. This is the string attached to the support, the fixed point. So you displace it through one direction, it will always accelerate towards the mean point. So it oscillates between the two extremes. Okay. All right. So this is the motion of a simple pendulum. Let's also look at the motion of a loaded spring. The motion of the loaded spring, or a helical spring. This is another simple pendulum.
Use your brain to slow down the green one. Slow it down, slow it down, slow it down. Telekinesis, make it stop. Let it go. Go ahead, let it go. And now to prove that it works, go transfer to the red one over here. Ready?
Okay.
Slow it down, make it stop, make it stop.
This is
no strings, no wires.
Oscillation. Free oscillation.
Use your brain to slow down the green one. Slow it down, slow it down, slow it down. Telekinesis, make it stop.
Okay. Then a loaded spring. The motion of a loaded spring. There's a spring. Then the load connected to the spring. Hence the name loaded spring. This is supported on a rotor stand. So when it is not oscillating, so the oscillator gives it an amplitude of oscillation, and it will do that repeated to and fro motion about an equilibrium position. So this is what we mean by the motion of a loaded spring. Okay. So let's go back to our discussion. Please, if you have any question to ask after the video, you can do so. Now, when a body is oscillating, its energy is not lost. Let's pick a simple pendulum, the motion of a simple pendulum. When it is at the fixed point or the rest position, there's it. When you displace it through small angle, the angle is very important. It will be oscillating, okay, between these two extreme points A and B. When it's at B, at a point A, this is one extreme. So kinetic energy must be 0 here. So Ke at the extreme is equal to 0. Ke is equal to 0. At the mean point, what will be P? What will be the value of Ke? What's the value of Ke at the mean point? Yes. Class, what's the value of Ke at the mean point? Oh, somebody should hurry up and then give me a quick response. What's the value of Ke at the mean point? Is it minimum? Is it maximum?
Maximum.
So Ke is maximum here. So what it therefore means is that when it is moving from the mean point, it is crossing the mean point with maximum kinetic energy. By the time it comes to the extreme, Ke is 0. So as the body moves from the mean point to the extreme, is the Ke decreasing or increasing? Will it be increasing or decreasing?
Decreasing.
So when it's moving, whenever it moves, it is moving to the extreme, the value of Ke decreases. There is a decrease whenever it's from the mean point to the extreme. Okay. Now, PE on the other hand is maximum at the extreme. PE maximum. Meaning that, and also 0 at the mean point. PE is 0 at the mean point. Let me draw it again to help you see well. So we have an oscillating body. This is the mean point. When it is given that small angular displacement, theta, it moves to the extremes. Fixed point or rest position. At the extremes, we know Ke is equal to 0. And at the mean point, the same Ke is maximum. Meaning, when we are moving to the extremes, Ke decreases. As we move to the extremes. If we are returning from the extreme to the mean points, from the extreme to the mean point, would Ke increase or decrease? Class, if we are returning from the extremes, would Ke increase or decrease?
Increase.
So this will be increasing direction. Okay. Then for potential energy, let me draw a different diagram to also explain this. Mean point, one extreme, another extreme. At the rest position, PE is 0. But at the extremes, PE is maximum. Meaning, as we move to the extremes, PE will be increasing. Don't forget, PE is due to, by virtue of the position of the body, okay? It's by virtue of the position. And if we are returning from the extreme to the mean point, we have PE decreasing. Decreasing. By the time we reach the mean point, it has decreased to 0. So look at 10. Look at the 10. PE is maximum at the extremes, but at that same point, at the extremes, PE is equal to maximum value, whereas KE is 0. Okay. Now, as we move to the mean point from the extremes, PE will be decreasing, whereas KE will be increasing. Okay. As we move from the extreme to the mean point, PE will be decreasing and KE will be increasing. Now, a decrease or a drop in one form of energy, is again in the other form, of energy. So as PE decreases from the extreme, as PE decreases from the extremes, KE increases. So the margin is the same. When one decreases by X margin, the other would increase by X margin. Okay. So that at the end of it, no energy will be lost. Total energy at the extreme will be equal to the total energy at the mean point, because a drop in one is a gain to the other. This is why for an oscillating body, its total energy is always conserved. Nothing is lost. A drop in one form of energy is a gain in the other form. So by the time we move from the extreme to the mean point, PE has decreased to 0, but KE has increased to maximum. And if we move from the mean point to the other extreme, okay, here KE is maximum, and as we move, PE will be increasing, whilst KE will be decreasing. By the time we move to the extreme, PE is maximum and KE is 0. So nothing is lost, but it is changed from one form of energy to another form of energy. This is the story of conservation of energy for an oscillating body. Please, if you have any question to ask, quickly ask before we continue. Mamiya, what's your question? Jojo.
Yes, I don't have any questions.
Elizabeth. So, Mamiya, if you are asked to explain why in the motion of a simple pendulum, energy is said to be conserved, how would you explain? In the motion of a simple pendulum, or yes, or let me limit this to a motion, simple pendulum, energy is said to be conserved. How would you explain?
Okay, so at the mean point, there's kinetic energy, maximum kinetic energy. And when it is extended to maybe the first extreme end so that you can let go of it for it to start oscillating, that's at that point, there's no more kinetic energy. There's potential energy, and that potential energy is maximum. And when you let it go, and it starts to oscillate, when it starts to oscillate, as it's nearing the mean point, the potential and the maximum potential energy we started with slowly converts into kinetic energy. And by the time we reach the mean point, it has been fully changed to kinetic energy, maximum kinetic energy. Then it decreases again. The kinetic energy decreases as it goes back to the as it goes back to the extreme point at the other side. Then it keeps going like that.
So basically, a drop in one form of energy is equal to a gain in the other form. Okay, so as this is dropping, the other form of energy is gaining. Okay, in that equal margin. So at the end of it, nothing will be lost. All right. So total potential energy at the extreme, at the extreme, is equal to the total kinetic energy at the mean point. At the mean point. All right. That is the story of the energy conservation for an oscillating body. Whether a simple pendulum or a loaded spring, that is what happens. Okay. Let's quickly draw the energy graph. The energy graph in terms of displacement of an oscillating body. So this graph is the energy graph with respect to displacement. So the vertical axis is for energy. The horizontal axis is for displacement. Okay, let me manage this line. And push this here. So energy against displacement. The vertical axis, let's label it KE and PE. And then, since the horizontal axis is for displacement, this point is equal to the amplitude. This is at a displacement of 0. And this other point is also the other amplitude. So positive and then negative amplitude. Let's have this point to be equal to the maximum energy, E for both. Now, if we are starting from one extreme, at the extremes, which of the energy is maximum? Class, at the extremes, which of the two energy is maximum?
Potential energy.
Okay, so if we are starting from the extreme, then potential energy must be maximum at that point. So maximum energy, and as we move to the mean point, for potential energy, the energy will be decreasing. Decrease. By the time we cross the mean point, hey, this my graph is not graphing. Let me draw it from there. So PE is 0 at the mean point, and as we move to the extreme, it will be increasing. Increase. By the time we get to the extreme, it has increased to maximum. Okay. Here, when we are starting from the extreme, it will be maximum and then decrease as we approach the mean point where y is equal to 0. So this is potential energy graph with respect to displacement. Then for kinetic energy, at the extremes, KE is 0. So as we move towards the mean point, it will be increasing. Increase. By the time we cross the mean point, it has increased to maximum. Then from the mean point to the other extreme, we have a decreasing kinetic energy. By the time we get to the other extreme, it has decreased to 0. So this is also a graph of kinetic energy. Their points of intersection are the point where their values are the same. So at the point of intersection, we have P equal to K. A line joining the two graphs indicates the total energy possessed by the body, the mechanical energy ET. So this is the energy graph with respect to displacement. Okay, so from the graph, you can clearly see that, oh, okay, then if this is for P, at the extremes, so at one extreme, another extreme point, okay, which one is maximum? PE is maximum and KE is 0. And these are the points where the two graphs are equal, okay? And KE is maximum whenever it crossing the mean point where y is equal to 0. And it is at that same point, potential energy is minimum. So this is the energy graph with regards to displacement. We can also plot the energy graph this time with respect to time for one cycle. So when we had or derived the equation for kinetic energy with respect to time, I think we had half m omega squared times a squared cos squared omega t. And PE, we had half m omega squared y squared. Okay, but because y is equal to a sine omega t, let's substitute this to have this in terms of potential energy in terms of time. So A squared sine squared omega t. Class, we can expand this to half m omega squared A squared, since cos, we can even plot the graph using this. Okay, so let's even use this. Let's not expand. Okay, so we are going to plot energy graph with respect to this time for one cycle. So the vertical is for energy, then the horizontal would also be for time. This is a graph of KE, the vertical KE and PE. Okay, they all have the same maximum value, half m omega squared A squared. Okay, so positive and negative half m omega squared A squared. We are plotting it against time. So when t is 0, when t is quarter of the period, we are doing it for one cycle. That is why we are dividing the cycle into 4 parts, a cycle into half t, and this is 3/4 of t, and then the full period t. This is time for a second. So let's plot it for kinetic energy first. So using KE is equal to half m omega squared cos squared omega t. Please don't forget, this can also be angles, 90, 180, 270, and 360. So you can either calculate using angles or using time. Now, when t is equal to 0, what will be the kinetic energy? We are using this to plot. So when t is equal to 0, what will be KE? Quick one. Let's quickly respond. And then when t is equal to 0, what will be KE? Or whoever has seen it can share with us. When t is 0, what is KE? Please, cos omega t is the same as cos squared omega t is the same as cos omega t all squared. Yes, Elizabeth, when t is equal to 0, what will be KE? Elizabeth.
Yes, please.
Okay, Rafa, when t is 0, what will be KE?
It will be half mv m omega squared.
So it will be equal to the maximum kinetic energy. Yes, this part.
Yes, please.
Okay. When t is equal to quarter of the period, or theta is 90, what will be KE? It is always easier when you are doing it in angle. So please, let's hurry up. When t is quarter of the period or theta is 90, what will be the kinetic energy? So you have half m omega squared times cos 90 all squared. What will be Ke? Mania.
Yes, please.
What will be Ke if theta is 90 or t is half the period? Okay, Elizabeth is ready.
Please, 0.
That will be 0. When theta is 180 or t is equal to half of the period, what will be Ke? When theta is 90 or t is equal to half, 180. Theta is 180 or t is equal to half of the period. What would be Ke? Ayo and Co contribute. And Nathaniel, Efia, Elsie, Fifi, Elizabeth.
Please, you get half m omega squared.
So maximum kinetic energy.
Yes.
Be using maximum kinetic energy. If you are lost as to how to calculate it, let me know. Okay, so let's do it for when t is equal to half of the period. So we are plotting it for kinetic energy. So Ke will be equal to half m omega squared cos squared omega t is the same as cos omega t all squared. Okay, I said this can also be represented as angle 90, 180, 270, 360. So it is always quick when you use angle. So if we are using angle for this, then half m omega squared cos of omega t is equal to theta, and theta is 180 degrees all squared. Cos 180 is equal to -1. So half m omega squared -1, but there is square. When you square -1, is the same as 1. So 1 times the maximum value is equal to this. So that is why at this angle 180, the kinetic energy is equal to the maximum value, half omega squared, the amplitude squared. I left out the amplitude, square of the amplitude. And if you want to use time, then half Ke would be equal to half m omega squared cos of omega is 2 pi on t times, this is half on t, half of t, or t over 2 all squared. This and this will cancel. 2 would cancel this 2. So you have this times cos 180. Pi is 180. So cos 180 degree all squared. And since cos 180 is -1, when you square it, +1 times that. So the value stands the same. Please, are we okay?
Yes, please.
Okay. Now, what will be the kinetic energy when t is equal to 3/4 of the period or theta is 180?
0.
That will be 0, because cos of 270 must give you 0. So everything will be 0. When t is equal to the period or theta is 360, what will be the kinetic energy?
Is maximum kinetic energy.
So maximum kinetic energy. So this time around, the negative will not come because the trig function is a square. So when we plot this for one cycle, this is what we have. So this is a graph of Ke for one cycle. For P, let's use this. Half m omega squared a squared sine omega t all squared or sine squared omega t. So when t is 0, what will be P? Class, when t is 0, what will be the value of P? Or when theta is 0? Yes. Oh.
This is 0.
For sine functions or graph would always start from 0. So you don't waste time. Okay. So when t is quarter of the period or theta is 90, what will be equal to the potential energy? What will be the value of the potential energy?
1.
About 1 times the peak value. So this would give us the maximum potential energy, which has the same value as the kinetic. So it will be here. When t is equal to half of the period, or theta is 180, what will be P?
Zero.
That's 0. Sine 180 is 0. And to a square of it, the value is the same. When t is 3/4 of the period, or theta is 270, what would be the value of the potential energy?
The maximum potential energy.
So the maximum value, the pattern is clear. And when t is equal to the period or theta is 360, what is the potential energy?
0.
That will drop to 0. So let's join our point. So this is also a graph for P for one cycle. And look at it. This is 0 at the mean point. Kinetic energy. Okay, no, this is not displacement. So you can denote it. So they interchange. PE is maximum here. KE is 0. Okay, KE is maximum here. PE is 0. So that interchangeability, okay, works. So this is the energy graph with respect to time for one complete cycle. The energy graph, meaning the energy graph, we have two different graphs. Either it is the energy against displacement or the energy against time or angle. So energy graph with respect to time / angle for one cycle. For one cycle. Please, class, do we understand what goes into the energy graph? So please master it, whether the with respect to displacement or with respect to time. Try and master, okay? Try and master so that if you are asked, you can quickly, draw it. And then, okay, so the energy graph brings us to the end of simple harmonic motion. But tomorrow I will try and then talk about practical application of this, how this is used in practicals. Okay, the practical application in our physics practicals, most of the mechanics experiments are under simple pendulum. So our mechanics experiment, usually we have the simple pendulum. We also have two, the loaded spring we have the cantilever, we have 4, the bifilar suspension, all these, and then the compound pendulum, the compound pendulum. All these experiments apply the principle of oscillatory motion, simple harmonic motion. So if you look at the video, this is look at the video on simple pendulum experiments. I'll also show you that of the loaded spring. Okay, so a string of length is tied to a metal ball. A metal ball, that's the mass. And then it is given small angular displacement to oscillate. Then you will be asked to time for a certain number of oscillations, maybe 20, maybe 15. So the time for the oscillation will be given to you. So you suspend this on a rotor stand, displace it as it was done, then count for X number of oscillations while you time. This experiment can be done without the use of the gadgets. You can get your time, calculate for the period without actually touching anything. That is why for experiments, when you understand the theory, is very, very important. Then we'll also discuss the applications of this. How do we use this? Okay, in engineering, do we always just oscillate and then count? It has engineering applications, which we'll also discuss. Then let's also look at the helical spring, the motion of the loaded spring. The mass spring system.
I want to illustrate simple harmonic motion using a mass spring system. We're suspending the mass from the spring, and the other end of the spring is attached to a fixed, rigid object.
Support.
The period of the motion is the time required for one oscillation. Boom, boom, boom. So it's the time between booms. And that's denoted by T in this equation. It's 2 pi, the square root of the mass of the that you're hanging on the end of the spring, and the spring constant K that's related to Hooke's law that we talked about before. The other important parameter is the amplitude of the motion. In order to determine the amplitude, you have to first figure out where the equilibrium position is. And that's the position at which this mass is not moving at all. So it looks to be at about 19 centimeters from the support up here.
So look at this mass spring system, okay? There is a ruler attached to it. The function of the ruler is to help you, one, determine the extension. When there was no mass suspended to the spring, this is it. Okay, there is the length. Please, can you hear me?
Yes.
Okay, so look at this spring, which has no mass attached to, meaning this is the original length of the spring. So if you want to calculate the original length, it is around, I think 6 from his rule. It's around 6, okay, centimeter. Now, when the mass is attached to the spring, look at the extension. The end of the spring is around, I think this is 16. So when you subtract the original length, which is 6 from 16, it means that the extension is around 10 centimeter. Okay, so in order to determine the extension when the mass is suspended, that is why the spring, the meter rule is attached to. Besides, he also wants to determine the amplitude. Concerning the amplitude, whoever is doing the oscillation, okay, determines the amplitude. Maybe I want this to move up and down around the equilibrium position. Here, this is the equilibrium position when there is no oscillation of the mass. So the equilibrium position is around 16 centimeter. So if I wanted to extend by maybe 2 centimeter, then I stretch it so that it will be around 8. Okay, and when you do that, this mass will be oscillating up and down, okay, above 6 centimeter. Every time, if there is no loss in energy, it will move up and down at a distance of 2 centimeter from when it is not oscillating, which is the 6 centimeter. So that is the reason why we have the ruler attached to the mass spring system. Let's continue to listen to what
the amplitude is defined as the distance between the equilibrium position, and I'm talking here about the top of the brass cylinder here, where it meets the meter stick here at about 19 centimeters. The amplitude is defined as the amount of excursion from the equilibrium position. So to create an amplitude, a motion with an amplitude of 1 centimeter, I'm going to want to move this mass 1 centimeter up and release it. And so now it's oscillating roughly between 18 centimeters and 20 centimeters. I could have done the same thing by moving it down to 20 centimeters. And then the overall motion is still 2 centimeters from top to bottom.
So this is why the amplitude is always constant. Because whoever is doing the oscillation determines how it must move up and down about the equilibrium position. So for an oscillating body, A must be determined by the oscillator, and the angular velocity omega is also constant because that's the uniform of a simple pendulum or a motion of a simple pendulum. Okay, so let's exit from this man and come to your Ghanaian man, Mr. Idria. So we'll be looking at the practical application of this. Okay, how many minutes do we have to go? We have about 10 minutes. So in the lab, for simple pendulum experiment, the materials given can be a rotor stand, You'll also be given a length of a thread, a known or a given length of a thread. You'll be given a pendulum bob, then the supports, then a meter rule. You also need a meter rule. All that, the intention behind this is that, or the theory is that, for a simple pendulum, the period is directly proportional to the square root of the length. And so long as we are on the surface of the earth, gravity is constant. So usually what we do is that you are given different lengths. You are given different lengths of thread. Maybe in that increasing or decreasing order. If it's decreasing, we'll begin with 100, then 90, 80, 70, and 60. Maybe the plan is to give you the length in terms of 10, 10, 10 intervals. Okay, so on your rotor stand, you measure this length starting from 100. Then you'll be asked to make it oscillate for a certain number of times, maybe 20 times. So you'll be given N to be 20, 15. Usually we determine the number. And then you're going to make this oscillate, and then you time for that number, or you determine the time for that number of oscillations. So in your table of values, you can be given T1, or you won't be given, but you must usually take your time twice. So T1, T2, then when you finish, you calculate for the average time, T average. Please, you also be given stopwatch, a stopwatch, because the stopwatch would help you determine the time. So T1, T2, and then you calculate for the average time. When you finish, you calculate for the period. Okay, so when you displace the pendulum bob through small angle theta in one direction, so you hold the pendulum bob, please, your measurement of the length is always taken from the center of the bulb. So if I'm measuring length of 100 centimeter, the measurement must be from the center of the bulb to the end of the string. So the length is always measured from the center of the bulb. So your ruler must be put at the center, and where 100 centimeter ends determines the length. Okay. Then you displace it through small angle and then count it for that number of complete oscillation. So a complete oscillation is always such that if I move it to this side, it must go and come, go to the other extreme and come. Okay, so I move it from the mean point to this side, it must go, come 1, 2, 3. Okay, so you are out of that numerous count. All that you are doing is that you want to determine the time for 20. So you can move it to one side, let it oscillate. When you are ready to count 20 out of that numerous oscillation. Let me go back to the video quickly and then share this with you. So he moved it to this side. I just want to count using what he's doing. Okay, so 1, 2, 3, 4. Okay, so anytime it comes back to where the movement or he moved it to, I have one complete cycle. Okay, so though it is oscillating, but I can choose to determine my time at any time which is ready for me. So let's start counting this. He oscillated. It's not by force that I should start counting once there's movement. I can just, okay, I want to start 1. So if you are ready to, the moment you start, you press on the stopwatch. 1, 2, 3, 4, 5, 6, 7. All that I need is that I want to determine 20 counts out of the numerous oscillation. In fact, the reason behind we counting that number of times is that actually we want the time taken to make one complete oscillation. And as I said, one complete oscillation must move from, I'm starting from A, it must move to B and come 1. So all that I need is the time taken to move from here to the other extreme and come back. But you cannot be so accurate. Okay, we can't be so accurate. So to prevent that, okay, instead of counting it only once to make mistake, let me count it for X number of times, and here 20. Okay, so I count and time it for 20. And when I finish, my period is equal to that total time I had divided by the number of oscillations. So if I counted it 20, okay, out of the lot, and I had 100 seconds, it is 100 seconds divided by the 20 count. And that will give me the period. And this will be more accurate than just counting it once. So that is the reason why we take that number of oscillations. Please, we'll continue this tomorrow and look at practical application of 1 or 2 and then continue. Is that okay? Mr.
Edia, please, the time there, are we using the average time or just any time?
We will use, good, that's a good question. It's because of the time, that's why. We have to use the average time. Okay, we will discuss it at length tomorrow. Okay. All right, so if you have any question, you jot it down for tomorrow and then ask. Okay. It's exactly 11:59. Class, this is where we end today's lesson. All right. Please revise and then create good questions so as to ask tomorrow. Okay. May the good Lord be with you. Take care of yourselves and bye-bye.
Bye.
Okay.
Bye.
Bye-bye.